Hello everyone, my name is Andrew Andrade, and I'm here on behalf of my team to talk to you about our fourth year design project, just informally, and go through our poster. We worked on the reuse of electric vehicle batteries for smart grid energy storage systems. Our team comprised of a multidisciplinary team from students in mechatronics, system design, and mechanical engineering, supervised by professors in mechanical, mechatronics, and chemical engineering. Let's begin with our poster, starting with the need. As many of you know already, we have a global reliance on fossil fuels to be projected to be there over the next 20 years. As you can see in this diagram, we are heavily reliant on oil, natural gas, and coal, with the renewables on the right-hand side very small, even after 20 years. It is scientific fact that the CO2 generated from burning fossil fuels leads to a greenhouse gas effect and causes global warming. This is a figure that just shows a complicated correlation between observed temperature and CO2 levels. The problem is that when we generate electricity during peak demand, or when there's a high demand for electricity, utility companies are forced to burn fossil fuels to meet that demand. Why is that? That's because renewable energy is inherently intermittent. So when wind energy only occurs when there's wind, solar only occurs when there's solar, and nuclear power is constant. Most nuclear generating stations have an almost constant power. The only real renewable that we can vary a little bit is hydro, but we don't have enough hydro generated electricity to power our growing energy need. The way that utility companies or the government deals with this is they try and create peak shaving, which means they try and reduce the amount of peak demand so that we don't have to burn fossil fuels. And the way they do this is through time of use pricing, meaning they make electricity to be more expensive during times in which there's high demand, which are in the evenings and the mornings, and are very cheap during the nighttime. That allows us to run very energy intensive things like our dishwashers or our washing machines and dryers in the nighttime when there isn't demand, so we don't have to burn fossil fuels. Concurrently, there's an increasing number of plug-in electric and hybrid vehicles that are producing battery waste. That leads us to the idea of a solution. What happens if we can pair the used electric vehicle batteries to store clean renewable energy through an energy storage system? And that's exactly what our project is. Our energy storage system comprises of the used electric vehicle batteries, sensors to measure temperature, voltage, current, as well as an embedded microprocessor which deals with this information through a dynamic model and applies logic to control relay switches that charge and discharge the battery. And we'll go more into the controls very shortly. We also have a high-level control server which logs the data in real time and provides a user interface, and we'll go into that more. The idea is that this energy storage system would be embedded into a smart grid in houses as well as commercial and industrial application. As such, the energy storage will be distributed and can also provide backup power if systems were to go out. But the main advantage is that it can allow us to create the idea of load leveling, meaning to allow the supply and demand to reach in unison. This is very important since in first world countries developed countries such as Canada and the United States, we produce more electricity than we need to prevent blackouts. As such, all that excess energy, we actually sometimes just waste it. It's not used. In Ontario, we actually send our excess energy to the United States and if we're not able to transport it in time, it actually just gets wasted. Let's talk about the first step in our solution. The first is battery modeling. Can we use these batteries? Are they still good? The answer to that, by looking at research, is that batteries that are disposed of in electric vehicles can still hold up to 80% of their original charge after they're disposed of. And why is that? That's because Electric vehicle batteries are disposed of when they cannot meet the vehicle voltage requirements, meaning that there's not high enough voltage to power a vehicle, but the batteries can still charge and discharge. And that gives us the idea, instead of disposing of them, we can actually repurpose them for energy storage in a grid system. The first step is to create a system model for repurposed batteries. Batteries are comprised of individual cells, which can be represented by a resistor, a capacitor resistor in parallel, and an impedance. The resistor represents the ohmic losses or the resistive losses as you pass current through the wires of the battery and through the chemicals. The capacitor represents the actual storage of the electricity and the energy. And the impedance is there due to the chemical reactions in the system. And not to go into the technical details of it, but as you vary the current and voltage in the system will behave based upon this model. And based upon literature and our own systems modeling, we're able to define this transfer function, which defines the voltage response of a given current. So you can control the amount of current that you passed into the battery, and it will respond to a voltage through this equation. There's the ohmic losses, and in addition, this is the effect of the impedance and the capacitance. And as you can see here, it's quite complicated and it's non-linear. And the way that we actually was able to verify this was looking at the step responses of a given current and comparing it with what literature said it should look like. And what we found is that actually the batteries do perform this way, and they actually do perform quite ideally. We can also determine the energy flow in the system through Coulomb counting. If we integrate current over time, we can calculate the number of coulombs that are entering and exiting our system. And as such, during the charging, we know about the amount of energy which goes into the system. And in discharging, we know the energy that goes out of the system. The difference is the energy lost. And that energy loss is generally due to the ohmic losses and heat. But the heat generation is as a function of both the temperature as well as the enthalpy changes of the battery that are a function of the state of charge as well as the current and voltage. So as you can see, the system is very non-linear and can be quite complex. We're able to actually simplify by taking the worst case energy loss and determining our thermal stability based off of that with a 3 times safety factor. So now let's talk a little bit about the electrical system. So this is just a very simplified system circuit diagram. In the center here, you can see the battery that's connected to ground. And we have 2 switches. One is to the charge circuit, and the second is to the discharge as well as a bypass. When electricity is cheap or is being produced with a low greenhouse gas emissions, we can actually charge the battery system, and at the same time, and that's from the utility grid, from the source, at the same time we will power our house, which is the load, as we're charging our battery. When electricity becomes expensive or is being generated uncleanly or not cleanly, we can discharge our system. And this is through storing energy in DC and through a DC to AC, and then discharging it in our house, which is the load here. For our project, we actually used Toyota Prius batteries that are consisting of individual cells that are 7.2 volts and 6.5 ampere hours. We have 5 of these parallel packs, which allow us a useful capacity of just under 500 watt hours with that 80% assumption that we talked about based off the research over here. And we have a nominal voltage of about 28 to 29 volts. And of course, we'll be charging and discharging, so the voltage will change. We also designed a mechanical enclosure to safely house the batteries and allow for adequate temperature control. So here's just a quick stress analysis, and the bending, of course, is more elaborated just to show that we did the stress analysis based off our simulation software. We also have fans which are running underneath, which you can see here in the cross-sectional diagram. We have fans which sit here and a filter to ensure clean air is entering our system. And the fans are spec'd based off the heat generation, which we calculated through studies in the first part of this project. This is a full photorealistic render of the model, and in a different video, I'll be able to show the video of the system. Here's a cross-sectional area, which I can kind of show you the different components. Here you can see our relay switches and our controller, our microcontroller BeagleBone, which we can talk about shortly. These are our our batteries, which store the energy. They're individual packs stored. This is our inverter. We have an emergency stop, and of course we have fans stored in our system. Now let's talk about the controls. So we use closed loop control, which is at the energy storage system level. So this is the low level control. And as we talked about, there is the inverter, there's the load, and there's the source. And the charging and discharging is a command given by our controller. Our controller is a BeagleBone Black. A BeagleBone is just a microcontroller that is Linux based. So it's similar to a Raspberry Pi, but it runs a little bit faster and doesn't have HDMI output, which is definitely not necessary for this project. So we have relay switches, and relay switches are very important as they create electrical isolation between the three systems. One is the sensors, two is the battery, and the third system is the inverter and the power to the load. By using relays, we're able to electrically isolate the systems such that if one electrical system fails, it doesn't affect the others, which is actually very useful. And of course, we do have an emergency stop as well as software stops in case of emergencies or the system is not behaving correctly. The switches connect to the batteries, which are then monitored through sensors. And we have three sensors. One's a thermal sensor, the second is current, and the third is voltage. For the thermal sensor, we're using a thermistor, which is placed in the center. We can monitor the individual cells as well as placed in the center so we can get airflow. And we also flow air through the bottom. It passes through the batteries to cool them down through convection and exits through the top. We also have a safety exit for the hydrogen that's actually generated by the nickel metal hydride batteries. Now let's talk about the controls. The state-of-the-art controls that we used. As we spoke about here, if you look at our transfer functions, our systems are quite non-linear. The non-linearity is also attributed to the batteries being repurposed and not being ideal, not coming out of the factory. We don't know what happened to these batteries before we received them. All we know is that they were used in cars beforehand. As such, there are three major components to our control system. The first is demand forecasting. As we talked about before, energy demand is cyclical. This is just an example, as you can see on the figure here. In the evening, during nighttime, we don't use that much electricity. As we wake up in the morning, when we turn on our stoves, make our breakfast, use a lot of energy. Midday, we don't use that much, and the peak of our energy is actually in the evening. When you turn on your stoves, you turn on your TV, you come home at night. That's when, in general, we use the most energy. As such, the demand is actually the signal for demand over time. The time series data is seasonal, meaning it goes up and down every day, but it also has a trend, meaning that in wintertime, for example, if you have electric heating, your energy usage will increase over time. In addition, there's an irreducible measurement error and daily fluctuation that occurs. As such, we use triple exponential smoothing. For those of you guys who are familiar with demand forecasting, this is just Winter's method, where we break the signal into three components. Again, the seasonality, the trend, and the residual or irreducible error. Moving means that we take the forecast over a weekly or a monthly basis. That's because your energy demand, of course, is dependent on the season and the week and the month. Auto-regressive means that we just are able to do it in real time. Regression basically means using features or using inputs and being able to do numeric prediction. So when we talk about regression, we're talking about numeric prediction based off of features. More of the machine learning term for regression. So auto-regressive means that we're doing regression or numerical prediction in real time. The next thing we do is state of charge. State of charge is very important as it defines when we charge and discharge our system. It identifies the amount of energy that we have stored in our system. So as time goes on, we charge and our energy increases, and then as we discharge, our energy decreases. And of course, we want to vary the charging current such that we reach our nominal voltage, we reduce our current, and we continue to charge until we trickle charge our batteries and eventually shut off, and then we discharge based off of demand. State of charge estimation is again done through Coulomb counting. Coulomb counting is just taking the integral of current or adding up all of the current over time. We also apply extended Kalman filtering in the state of charge estimation. Another method to determine state of charge, just a different estimate, is actually using voltage. The problem with voltage is it's not a very good measurement as there are ohmic losses and fluctuations in the voltage. So if you look at the voltage over time, you can see there's actually a voltage drop and increase as you do a step change of the current. As such, extended Kalman filtering allows us to use the predict and measure to actually reduce the steady state error of using the voltage method for state of charge. So by pairing both the Coulomb counting and the extended Kalman filtering, we can do better state of charge estimation. And of course, we didn't come up with this technique we actually were able to find this being used in industry and in research, and we just follow the methodologies. And again, both the exponential smoothing and the Kalman filtering and the other techniques that we use were based off of software libraries. We particularly used Python and used scikit-learn to do a lot of it. The next thing that we have is remaining useful life. And remaining useful life is quite a controversial thing that is not very well understood. Based off Professor Fowler, who's our supervisor, his research up here, we're able to determine the capacity fade as a function of the ampere hour processed. So on the x-axis here, you can see the capacity fade, or the reduction in capacity as ampere hours go over time, or as coulombs go over time. What that means is as we charge and discharge the battery degrades, and that process is irreducible, unfortunately. But by predicting the amount of ampere hours we process, we can then use this relationship to determine the remaining useful life. And the way we do that is through a support vector machine. So that's generally used as a high margin classifier. But you can also apply it to nonlinear regression. And scikit-learn actually has a really good implementation of this. The reason that we use the RGF implementation of the support vector machine is just because it's non-linear and it deals well with ampere hour process. So we apply different machine learning techniques for regression, and based off of the grid search and the cross validation that I did, we found that support vector machines work pretty well. So for it, we again did auto regression to determine the charge and the ampere hours being processed. So the charge and discharge, we did numeric prediction and determined the remaining useful life. These three are very, very important as they are a function of the heat generation. So there's this idea of RINT characterization, or internal resistance. And the internal resistance on a battery system is a function of the state of charge, the temperature, enthalpy changes, the remaining useful life. It's a function of all these different features of the battery, and it's very non-linear. And the idea is that you want to operate your system when the internal resistance is the lowest. That means that the energy loss due to ohmic losses is the least. And as such, you also want to vary the temperature based off of this. And since the system is non-linear, fuzzy logic works extremely well, and we're able to use fuzzy rule sets based upon the heat generation, the demand forecasting, the state of charge, and the remaining useful life. And I'll make another video of the system operating in real time and give you a demo of kind of how the fuzzy logic works. Let's finish off the poster now. So let's just talk about the system being designed to scale. So again, we have a very similar model of the Internet of Things. So we have our system that's connected through a pipeline. You could say it's the cloud. I guess our control server sits on a virtual machine on an online web service. And so we have servers that are able to scale and are connected through a pipeline. Data pipeline allows us to transfer data in real time. What that means is that our energy storage system can actually use the fuzzy logic and the charge and discharge and work on its own. but can also send that data in real time to a high-level server. So the high-level server can do the very expensive computational tasks that are not critical to the day-to-day to the minute-by-minute or second-by-second operations of the system. So the demand forecasting and the policy change at the grid level can be done through this control server. We also have data storage through SQL, or structured query language server. So we just store the data over time. The reason that we separate our system into these three components is the energy storage system is able to operate independently. So even if we lose internet connection, the energy storage system is still able to charge and discharge safely, and can use pre-computed values for demand, as well as energy price and other policies for when to charge and discharge. The control server can work. That allows us to be controlled via user interface, and we also are able to store the data in real time. And again, I talked about being controlled through a user interface that you can view it. And again, the actual other video that we'll create with our system functional will demonstrate this functionality. So in that video, we'll show how we can charge and discharge the battery, and how by using the idea of arbitrage, we can save people using the system money. So as we talked about before with the three-tiered price model, what happens if when the electricity is expensive, we actually just discharge our system, and when the electricity is cheap, we charge it? As such, we are able to buy electricity at the cheapest price and use it when the price is more expensive. Using that arbitrage, we're able to save money. But more importantly, and this is, I guess, a figure of the monthly savings, you can see here before an energy storage system, without it and with it, how you can save some money. Our real-time system shows this a lot better. But that money savings and the actual tax incentives to make such a system possible is actually significant greenhouse gas emission savings and money savings through at the grid level. So I talked about load leveling and the mismatch between supply and demand. If you're actually able to have a distributed energy storage system, you're able to store energy. And you're able to charge and discharge. So as you can see here in black, this is our demand, and our blue is our supply. So we can have a constant nuclear supply, and we can also get the intermittent supply from other renewables. As such, when the demand exceeds the supply, we can discharge the battery systems at a grid level, and when the demand is less than the supply, we can charge our systems. That means the excess energy that we produce is not wasted, and we can actually create load leveling. And if this is actually at a grid level in Ontario for a winter month, and this is just using actual real data from the energy board, we're actually able to show that we can replace about 131 gigawatt hours of demand normally supplied by natural gas. So that's just a component of natural gas, eliminating about 143 megatons of CO2 emissions in only 1 month, just in Ontario, which is quite substantial. And this is a simulation of the CO2 emissions also done by Professor Fowler's research team. Here we can see if you have a traditional fossil fuel or gas-based, or not gas, but petrol-based vehicle. And here you can see this is an electric vehicle equivalent. You can see the CO2 savings here. And then if we repurpose them after their useful life over the next 10 years, you can see that we have substantial CO2 emissions. And this is at a larger grid level. So throughout our project, we were able to build a prototype that successfully demonstrated the ability to, one, repurpose the electric vehicle batteries, and two, charge and discharge to create a distributed energy storage system. So definitely check out the video of our system operating in real time. And here are some of the references from the figures. We also have a report which outlines the details of the methodologies we used throughout the things that I talked about. I hope you enjoyed this video. Thank you.